These kinds of questions are low-hanging fruit. They're not going to ask them on the exam like this. So it would be a joy if they did, but they just want the momentum and the kinetic energy. The way this exam sounds, they are not going to ask the questions like this. Even though they're using this as an example, I would expect that we won't see this kind of straightforward calculation. They're going to have you do more explanation. But, momentum is just MV, so we're talking 0.2 times 3 or 0.6 kilograms meters per second. And kinetic energy, 1/2 MV squared. So, that's going to be still 1/2 times 0.2 is 0.1 times 9 or 0.9 joules. So that part was pretty straightforward. I would not expect that on the exam. Question B, sure. Question B would be where I would begin the problem. And that's going to ask you, what is that says determine the following for the combined masses immediately after impact. So what we're being suggested here is that our first box, that's not going to work. Come on, be my friend here for a minute. There. Put you back up there. And I'll get you a little box, but you're right there. So this box strikes and combines with the first box. And so the system now is going to have some velocity this direction. And, I know I could ask this, and I probably should, but a perfectly inelastic collision, correct? So because it's a collision, and it's considered a perfectly inelastic collision, we know that the momentum during the collision will be conserved, but the energy will not be. So when it asks for what the momentum is immediately after impact, it's really not asking me to do very much. It's got to be 0.6 kilograms meters per second. Right? The momentum of the system hasn't changed, so don't sweat questions like that. But sweat the next one where it says, what's the kinetic energy after impact? Because you might be lulled into like a little bit of security. Well, clearly if the momentum didn't change, the energy did change. We know that this system slowed down dramatically after the collision. The little box hit the big box. The big box is big, and therefore it's going to not travel at the same speed. There is a force on both. We don't have to get into all the explanation, but remember, our exam is likely going to require explanation. So me talking this out is me anticipating the real questions we're probably going to see on the exam, which are going to ask you things like, was there a force experienced by the boxes? Was the force the same experienced by the two boxes? Things like that are things I think you should be considering when thinking about how they're going to be interpreting the question. Remember, less math, more explanation. So the fact that they're asking for the kinetic energy, there is some kinetic energy absorbed in this collision. In order to figure that out, we're going to need to find the velocity of the system after the collision. And it's a collision, so it's the before case. And I know I'm redrawing this, but this is because, I want to be thorough, and we have a lot of people who aren't coming to class, about 15, of course, across the course of the day. So I'm trying to make sure that I'm doing as much as I can to record that. So I'm thinking we still have our 0.6 kilograms meters per second here, but now the new mass of our system is going to be 0.2 plus 1.3, and that's times my new velocity, or VF. Any questions about that? Alrighty, so all we have to do is have 0.6 divided by 1.5, and that's going to give us our new final velocity, and that sounds like it's going to be, 0.4. So this is not the answer to the question, but we need to have the velocity after the collision. It's dropped down dramatically now from our 3 meters per second to our 0.4 meters per second. Just barely schooling along. So our next job is to use this to figure out the kinetic energy, and I'm kind of running out of space, but I think you guys would be okay for right now if we just found the kinetic energy over here, which is just going to be 1/2. Now, when you do our M, don't make the mistake I just made. M is still 1.5. We have to include the entire mass that's moving here, because that's the mass of the system, and it asked about the system, times the total the new velocity, 0.4 squared. So 0.4 squared is 0.16. Half of that is 0.08. So 1.5 times 0.08. And you're going to have to do that because I don't have my calculator available, but you understand the calculation isn't that important. Getting to the answer is, and make sure we don't forget energies in joules. We don't want to screw up something simple like not putting the units down. All right, so that's kind of the low-hanging fruit of this question. Any problems with this? Anything you want me to review about that? Feel pretty confident? All right. So after the collision, two masses undergo simple harmonic motion about their position at the impact. So this is, I told you before that simple harmonic motion, if it makes its debut in the test somewhere, they're really going to just use it as kind of little pieces here and there. They're asking us to find the amplitude of the harmonic motion and the period of the harmonic motion. And, both of these are things that really had nothing to do with the beginning part of the problem, except that if we want to figure out the amplitude, we do have to recognize that whatever kinetic energy the system had at the point of that collision, this has to be the energy that gets stored in the spring when x goes to the amplitude. Right. This is not a harmonic motion question. This is a conservation of energy question. Although energy is not conserved during the collision, the spring mass system conserves energy. Remember, we have to be able to separate the parts of our problems out and recognize when energy is conserved and when it's not. Collisions normally don't conserve energy unless we have that special word, right? They have to say elastic. Now, the truth is, they conserve energy. They just transform it into something that we can't track. But after the collision, we can track the energy. The energy is going to be leaving the motion of the boxes and going into the spring, and that's how we figure out the amplitude. So we already just calculated the kinetic energy. All you have to do is recognize the spring constant is 100, plug it in there, and figure out the amplitude, which has nothing to do with question D, determine the period of the harmonic motion. So let's take a look at question D because, as I said before, they just tend to throw in harmonic motion questions. So you have an equation sheet. That's a plug and chugger. That's really just it's not very interesting, and it's not particularly worth a lot of time. And that also means that they're not going to put a lot of points behind it. Biggest mistake people tend to make is putting the wrong mass in there because they forget about the collision portion, but the entire system is what's oscillating, so it has to be the entire mass of the system. Now, again, this problem not particularly interesting. Remember, this answer's in seconds. But I'm trying to think of the actual tests that they're going to be asking, and these don't seem like the kind of questions I would normally expect. Not the way they've been describing them. So there are other things here that I would expect them to do to try and maybe spice it up. And we've seen kind of the way they've brought these questions into AP. So let me back that up because that sounded a little bit as if I'd never talked before. So let me try that a little differently. The question like this is a very straightforward, not convoluted, point-by-point trip through conservation of momentum and conservation of energy. It didn't veer from it. It's not in the vein of the two kinds of questions we're expecting. The biggest problem I'm finding is the examples they're offering us for test-level questions don't mimic the things they're telling us are on the test. For example, did we have to write a paragraph here anywhere? Was there any point where we had to take a look at a student's idea about a problem and apply a theory to see if the student was correct? So this problem doesn't fit the mold, but they're saying that this is what we should expect on the test. So my incentive to you is to consider perhaps what would be a follow-up to this question, a way that they could work in the things that they're talking about. And I have 3 ideas about that. So let's take a look at these 3 ideas and see if you can kind of see what I see about them. One of them is to consider this problem, which has actually been on the AP exam and is considered one of the qualitative, quantitative questions. It looks like this, and I have to get my colors all right here. There we go. It imagines a system where there's a spring mass, like so, And the mass has been pulled back to some starting position. So we start here. Oops. So it's pulled back a distance A and is then released. Now, again, no big deal. Whatever mass it has, whatever spring constant we have, we know that we now have a harmonic oscillator. And you remember the problem we did where they dropped a mass when they dropped the mass on top of the mass when it was at one of its when it was at the amplitude. Do you remember that? Or no, it dropped it in the middle when it was at the maximum velocity. Do you guys remember that problem we did in class? If not, because Haley might not remember, let's just do a quick reminder of the two ways they could then branch this problem out. The straightforward collision we saw, I don't think we'll see. I think we'll see something like this. The mass is released. It passes through equilibrium. And we all remember that when it passes through equilibrium, that's when it's at its maximum velocity. And as it passes through equilibrium, they drop another box on it that sticks to it. So they do it right at equilibrium. That creates a vertical inelastic collision. It's exactly like the problem we just did, except that in this example, this bottom box is the one that has momentum before the collision. This top box does not have momentum before the collision. And this collision will take energy out of the system just like it did before. So the question's not going to be what's the new amplitude or what's new energy. The question's going to be what happens to the amplitude and why? That's the way they're going to ask the question now. Because they're going to be looking for you to come up with several points of reasoning. First, they'll probably have like a checkbox. The amplitude will be the same, the amplitude will be more, and the amplitude will be less. And you know you won't get any points for the checkbox. But then they're going to follow up with justify your reasoning. And they're going to be looking for you to connect the dots, right? This collision is inelastic, so the velocity after the collision will be less. Because there's less velocity, there's less kinetic energy. Because the box spring system still conserves energy, less kinetic energy means less potential energy. So the amplitude will be less, right? A full paragraph connecting how the change in momentum creates a change in potential energy of the spring. Now, we talked about this problem about 3 weeks ago, right? God, has it really been 3 weeks of Zoom school? 4 weeks of Zoom school? I have no idea what day it is anymore. I mean, the only reason I know it's Thursday is because it's my birthday. So this is one way for them to ask the question. And we talked about that way. But what about this one? What if instead they release the mass right there and we wait till it makes it to this point, a distance A on the other side of equilibrium. At this moment, the velocity is 0. And all the energy is in potential. It's at its max. What if we dropped the mass on it now? What would that do to the system? Now, this problem is more interesting because A, you've never seen it before. And B, it offers us a kind of an odd alternative to the one we just saw. For example, is this a collision? It seems like it's a collision. It has all the hallmarks of a collision. But is it a collision? Is either box moving sideways before the collision? And since the answer is no, this actually would not be treated as a collision because there's no horizontal velocity. This box would simply land on top of the other box. It wouldn't affect the current velocity of the system because the current velocity of the system is 0. This would affect stuff though. The inertia of the system suddenly changed. So can you think of what other things would change because the inertia changed? If you can, that'd be fantastic, because it's not an easy question. In fact, just thinking about it, I know that there's about 3 things that change because of this. Now, what I'm going to do is I'm going to send you guys out into a breakout room for just a minute. And I don't need the explanation. See if you can't kind of bat around what things might have changed and what things haven't. Okay, we've talked about lots of things today. We've talked about period, momentum, kinetic energy, velocity, amplitude. These are all things we've talked about. Can you figure out which of these might change because of this and which of these things won't? All right? So you got 3 minutes in the breakout room. So let me get your breakout rooms all set up. And like I said, nothing but you get in just the 3 minutes. It's going to be super fast because we're kind of at the end here. So here you go. And I will see you in like 3 minutes. Skylar was back. She was back first. All right, everybody shuffling in. I know. Come on, clear out of them rooms. Let's get everybody back in here. We're missing like 3 people. Who's still in the room? We have a whole room that didn't clear out. Chloe, Kyle, oh, here they come. Wow, it's almost like being in a real place, like a real classroom. Not really, not even close. All right, so I'll take volunteers. Who thinks they know? Go ahead. Haley? Okay. Perfect. So she's got one. Her group did great. Somebody else give me another one. Can you talk about why? Okay, so there would be a change in momentum in the system. That is true. What else we got? Nobody else. Come on, take a risk. Oh, somebody typed it. Kinetic energy. Ivan, do you think you can give me like one sentence as to why? I hear him typing. Can you guys hear him typing? I know, I'm so excited. I'm giddy. Who knows what he's going to say? Funny as I can see him typing. It's like weird. You need to buy him a microphone. Just get him a mic. Just talk. He does have a lovely singing voice, we know. Yeah, so there. Now, we have to understand something here, and all these things that we're saying are true. The amount of energy in the system, though, here's where we're going to have a problem. And this is why the kinetic energy might be an issue. The total energy of the system didn't change. The mass did suddenly change. That part's right. But I don't think the kinetic energy changed. I think the velocity is going to change. Vmax, definitely going to change. But the amount of energy never changed. We will still be setting this equal to 1/2 mv squared. And the mass has suddenly increased, which means that we're going to have a change in the max velocity, not because of conservation of momentum, but because of conservation of energy. So there will be a huge impact on the velocity of the system, which will affect the max momentum of the system, but the energy is unchanged. So the kinetic energy wouldn't have changed. And I think that was one that would trip people up, because the amplitude also doesn't change. The amplitude is going to stay the same because the amount of energy in the system didn't change. And remember, the mass landed on the other mass when all the energy was in the spring. So when it gives that energy to the masses, it only has so much energy to give them. See? Went the other way on you. But that's okay. I was learning experience here. All right, so we have reached the end of the day.